Hello, Math 1224. This is Dr. P, and this is Lesson Launch 1201. I wanted to give a brief intro to two ideas from physics that we're going to be talking about in class, and those are the ideas of mechanical energy and work. And I'm putting work in quotation marks because work in physics means something very specific. It doesn't mean the same thing that it means in everyday vernacular. So to set this idea up, these ideas of mechanical energy and work, I want you to consider a tomato. So let's suppose we got a tomato sitting on a flat surface like the floor. Okay, so you've got a tomato. This tomato has some mechanical energy in it right now. Perhaps not very much. But suppose I take that tomato and I lift it up and put it on the table there. All right. Now I tried actually dragging that object around using Explain Everything's Move tool. That didn't work very well, so I'm just going to draw the tomato again up here. Okay, same tomato. Ignore the fact that it looks a little bit different. Okay, so anyway, in the process of taking the tomato and putting it on the table, I've actually added to its mechanical energy. In particular, I have added to its potential energy. That is gravitational potential energy. And that's one of the main types of energy we're going to be talking about in this, when we do physics in this course. We're not going to do a whole lot of physics, but we are going to do some in this section. And in this case, we're going to talk about gravitational potential energy. Now, let me try and make some case for why we should think of this object as having gained energy, even though we just picked it up and put it on a table. The reason this object has energy is now this object has some potential for motion. Now, if you just leave it there on the table, it's just going to sit there. But if you were to wobble that a bit and that tomato were to roll over here and then roll off the table, it would then drop to the floor. And then you would see the tomato in motion. So we think of this tomato as having some potential for downward motion, even though right now it's sitting on a table. That's what potential energy means, roughly, is that it's gone up and it could come down at any time. Okay, now here's another scenario. I'm just going to move this frame over here. Okay, so again, same tomato. Now let's suppose that your little brother comes in the room and kicks it. So there's a foot, and your brother's going to kick the tomato, and let's suppose that the tomato holds up. It doesn't splatter all over everything. And now that tomato is an airborne object. The art part of this video is actually kind of fun, I have to say. This is one of the more fun ones I've done. I'm not just writing down integrals, I'm drawing pictures of, like, cartoons of tomatoes. Anyway, that tomato is now in motion. And because it's in motion, it has something called kinetic energy. So by kicking the tomato, your little brother has added kinetic energy to the tomato, as well as gravitational potential energy. It's actually both of those that have been added to the tomato. So this tomato now has some gravitational potential energy and some kinetic energy. Okay, so in this initial state, let me just zoom this out. In this initial state, the tomato has some amount of energy. We can never say exactly how much. There's no actual answer to the question, how much mechanical energy does something have? It's all relative to some base point. So we could say at this time, we could define this tomato as having total mechanical energy 0, and then by putting it on the table, we add some gravitational potential energy. So now the tomato has positive mechanical energy, and by kicking the tomato, perhaps we give it even more positive mechanical energy. But now I want to talk about what it takes to give an object mechanical energy, because in both cases we've added some mechanical energy to it. So by picking up the table, picking up the tomato and putting it on the table, we have done something called work. We have performed work on the object. Now the way that work works in physics, pun totally intended, is we apply some force on an object as it moves some distance. Okay? And when we do that, when we apply a force on an object as it moves some distance, the amount of work done on the object is equal to the force we've put on the object times the distance it's moved. If the motion and the force are in the same direction. Are in the same direction. And I'm claiming that under those conditions, the amount of mechanical energy added to an object is going to be equal to the force times the distance. Now, that's kind of a mysterious claim, and unfortunately, I'm not going to be able to prove it here. If you want to see a proof of that, you should take a physics course, take a good physics course, preferably a calculus-based course. But let me try and make some case for why the amount of work done on the object should depend upon both of these things, the force and the distance. Why should it be proportional to both of those? Okay, so to make the case for that, I'm actually going to use another example. I'm going to imagine a little push cart, which has some mass and therefore requires some force to move. All right, and I'm going to imagine a person pushing on the cart. All right, now let's suppose that this person applies a force of, let's say, 100 newtons to this cart and applies that force through a distance of 2 meters. So what's going to happen then is the cart's going to accelerate, and by the time this person is done pushing the cart, that cart's going to be moving forward at some constant velocity after the person stops pushing. That constant velocity, that is the object's kinetic energy. The kinetic energy is actually 1/2 times the mass of the object times the speed squared. But just think of the kinetic energy as being rather large if the object is moving fast, and rather low if the object is not moving or if it's moving very slowly. Okay, so by pushing the cart 2 meters with a force of 100 newtons, this person has put some force, not some force, put some energy, mechanical energy, into the cart, therefore has done some work. Now, let's suppose that instead of pushing it 2 meters, this person pushes the cart 4 meters, still with a constant force of 100 newtons. So now the cart's going to move further along while this person's pushing it. Well, if you imagine pushing something even further, imagine this being a really heavy object. If you push it farther with the same force, then by the time you're done pushing, that object's going to be moving faster, therefore have more kinetic energy. So that's why the distance matters, is if you push it through a greater distance with the same force, you're going to accelerate it more in most cases. Now, what about the force? Well, the force is just a measure of how hard you're pushing. So if we were to push not with a 100 Newton force, but maybe with a 200 Newton force, that's going to cause the cart to accelerate faster. And so if you push it through 4 meters with a 200 Newton force, by the end of this process, it's going to be moving even faster. I wouldn't say twice as fast. I don't think that's quite right. But we'll be moving faster. So anyway, that's just a sort of a rough argument for why the amount of work should depend on the force and the distance. Okay, let me say one more thing, because actually maybe a couple more things. One thing is I want to say a little bit about what things look like if the motion and force are not in the same direction. Now, the case in which the force and the distance may have nothing to do with each other, like maybe your force is this way and your motion of the object is this way, we're not going to cover that in this course. This is not in Math 1224. Although you probably will encounter this in Calc 3, so I don't want to ruin that for you. But I do want to say a bit about what happens if these are in opposite directions. So what if these are in opposite directions? Okay, so for this example, again, imagine a cart. Now this time I'm going to ask you to imagine the cart already moving towards you. So you're here and you're bracing to stop this cart using your brute strength. Okay? So if this cart is barreling towards you, and let's say that you're wearing ice skates, and this is an icy surface here. So let me pick a color there. Okay, there we go. No, wait. Okay, sorry about that. So let's say this is an icy surface, and you're wearing like frictionless shoes. So that when this cart meets you, you are going to push on it, but the cart's actually going to push you back a little bit. So what's going to happen in that case, so the cart's moving this way, what's going to happen in this case is you're going to push on the cart and you're going to apply some force, maybe 100 newtons again, but the cart's going to move this way while that happens and you're going to move this way. So now, this force times distance calculation, it changes a bit. The force is in a rightward direction, but the motion of the object is in a leftward direction. So we think of this as giving us a negative number. So in this case, the work is negative if the force and the distance are in opposite directions. The reason for that is, this time the force that you're applying to the object has the effect of decreasing the mechanical energy of the object. You're decreasing the mechanical energy because initially this cart's coming at you with some kinetic energy, and you're slowing it down. So you're decreasing its mechanical energy. So you've done negative work on the object, even though it feels like you've had to work pretty hard to stop it. We actually consider that doing negative work on the object. Anyway, that's one note I wanted to give. The other note is, what about the case of potential energy, gravitational potential energy? So let me come back up here. I think the tomato example worked just fine for this, in fact. Okay, so let's imagine taking that tomato once more and picking it up and putting it on the table. So in this case, what you're doing is you're applying an upward force of, that force is going to be equal to the weight of the object. And I don't know how much physics you all know, but in physics, weight and mass of an object, they're not the same thing. The weight is equal to the mass of the object times g, which is the acceleration due to gravity. That's 9.8 meters per second squared. So those two things, weight and mass, are related. Sorry, that should be meters per second squared. Weight and mass are related, they're proportional to each other, but they've got this factor between them, that the weight is equal to the mass times acceleration due to gravity. And that weight, that tells you how much downward force gravity is exerting on the tomato. That means that in order to lift the tomato, you have to at least match that force, that downward force due to gravity. So you're going to match that by applying a force equal to the weight of the tomato. So you apply that upward force and pick up the tomato and move it through this distance, whatever the distance is between the ground and the table. Okay, drawing tomatoes is fun. It was by far the highlight of this video for me. Anyway, in that case, the work that you do on the object... Oh, by the way, this is kind of unfortunate. I'm using W here for weight, and then over here in this other formula for... where was it? Actually, I never use W for work, but I usually use W for work. So I feel like I should probably, instead of calling that W, I should call it F. F equals mass times the acceleration due to gravity. So we'll refer to weight by F for force. So the work is going to be equal to the force, that's the weight of the tomato, times the distance through which you're lifting it. In this case, I'm calling that H. And that's the basics of how we calculate work. It's equal to force times distance. In the case that we're lifting an object, it's usually the weight of the object. The weight of the object times the amount of height through which we're pushing it. But again, that only works if the force is constant and if the height through which you're moving the object is constant. So if you're dealing with something of constant mass or weight and moving it all through the same distance, and that force and that distance are both in the same direction. This is calculus class, so we're going to deal with a case in which sometimes an object does not have total uniform weight, Or maybe the object is not a point object. It's an object where maybe it has some height to it. Like, let me give an example here. Like maybe there's some banner hanging off the side of the table and you want to pull it up. Well, in that case, you're going to have to apply some force, but the distance through which you push this part of the banner here is going to be rather large, whereas this part of the banner doesn't have to move through so great a distance. So anyway, the point is, our presentation is going to deal with what happens when there's some variation in these things, either the weight or the distance or both. Okay, anyway, I know that was kind of a jumble, but one thing that I would appreciate would be if you left for me a note telling me how much exposure you've had to these ideas before, because I can imagine if you've had none, this might not have been the perfect intro. But just let me know what you understood from this, and then we'll start there in class. Thank you.